Hello students, today we will study P-type extrinsic semiconductors. Basically, there are two types of semiconductors, intrinsic and extrinsic semiconductors. Extrinsic semiconductors are classified into two more types, P-type and N-type semiconductors. Basically, intrinsic semiconductors are called pure semiconductors, whereas extrinsic semiconductors are known as doped semiconductors. Today we will see the details about P-type semiconductors. P-type semiconductors are also known as acceptor type of semiconductors. So how P-type semiconductors are formed? When a pure semiconducting crystal of germanium or silicon is doped with the trivalent impurity like boron, indium or aluminum, then P-type semiconductors are formed. So what are trivalent impurity elements? The elements which has 3 valence electrons are called trivalent impurity elements. So boron, indium or aluminum has 3 electrons present in their outermost shell, hence they are trivalent element. So suppose this is a pure semiconducting crystal of silicon, contains large number of silicon atoms. Okay, neighboring silicon atoms are bonded together by covalent bonds. So this is a pure semiconducting crystal of silicon. Suppose this pure semiconducting crystal of silicon is doped with trivalent impurity element. We are considering here trivalent impurity element of aluminium, and we know that the atomic number of aluminium is 13 and its electronic configuration is 283. Since there are 3 electrons present in their outermost shell, hence it is called trivalent impurity elements. Why it is called impurity elements? Because we are going to dope this pure semiconducting host crystal with this foreign element, hence it is known as impurity to this host crystal of silicon. Okay, so suppose this is a aluminium trivalent impurity which has 3 valence electrons, and these 3 valence electrons are shown by this green circle. Okay, now I am showing the animation. Suppose this silicon atom of this crystal is replaced by trivalent impurity element of aluminium, and we know that the valency of silicon is 4, hence it has 4 valence electron, whereas the valency of aluminium is 3, it has 3 valence electrons. Okay, when we replace this silicon by aluminium, so what will happen? The 3 valence electrons are involved in the formation of covalent bond, but the fourth covalent bond remain unformed. Okay, this fourth covalent bond is not formed, so this non-formation of this covalent bond is equivalent to a hole. Okay, so it leaves behind one hole. Okay, when this one silicon is replaced by the trivalent impurity of aluminum. Okay, so what happened next? When we increase the temperature beyond 0 degree Kelvin, okay, so the electrons present in the covalent bond, as we seen in the intrinsic semiconductors, the electrons present in the covalent bond, okay, will be free. And suppose one free electron from this covalent bond, okay, is started moving, and suppose it is encountered with this hole, again it combines with this hole, and again it is responsible for the formation of covalent bond. Okay, when the electron is released from that covalent bond, again hole is formed, but this hole is formed without the generation of electron. Okay, because that electron, when released from the covalent bond, it combines with this hole which is already present in the silicon crystal. So again this covalent bond will get formed, and again hole is formed here. So the hole is formed here without the generation of electron. Okay, whatever we have quoted in the diagram, now we will see on the slide. So suppose trivalent impurity like aluminum has replaced silicon, 3 valence electrons of aluminum forms covalent bond, but 1 electron falls short to complete 4 covalent bonds. So non-formation of one covalent bond is equivalent to a hole. We have already seen in the diagram. When an electron from neighboring silicon atom acquire energy and jumps to form the bond, leaves behind again hole. Okay, that we have already discussed in the diagram. Okay, so suppose when the electron from neighboring silicon will come towards this aluminium and this fill this hole, so aluminium get extra electron, but aluminum has three valence electron. When we get extra electrons, okay, so this aluminum is converted into aluminum ion and will get a negative charge because of that extra electron. Hence aluminum is accepting the extra electron. Hence aluminum is known as acceptor atoms, and that aluminum will convert into the aluminum ion. Okay, so aluminum atom get additional electron and become negative ion, and the aluminum position is fixed in the crystal. Hence it is known as immobile ion, and the hole can move freely in the valence band. The hole can move freely in the valence band, and the impurity atoms, like we discussed about the aluminum, the impurity atoms which accept electrons from valence band are known as acceptor atoms, and they produce the holes without generation of electrons in the conduction band, that we have already seen in the previous slide, okay, through that diagram. So now we will move towards energy level diagram of p-type semiconductors. So energy level diagram of p-type semiconductor consists of valence band. So this is valence band, contains valence electrons which are present in the silicon atom, and this EV top of the valence band is denoted by EV. Now the conduction band is present at a certain higher energy than valence band, and the bottom of the conduction band is denoted by EC. Okay, this energy level diagram we have already seen in intrinsic type of semiconductors. Okay, now we know that the energy is increasing from valence to conduction band. So conduction band have higher energy than the valence band. Okay, so the energy level diagram of p-type semiconductor consists of one additional level. That level is called acceptor energy level, which is denoted by EA, and the acceptor energy level consists of acceptor atoms. Okay, as we saw the example of aluminum. So suppose aluminum are acceptor atoms, and those are present in the acceptor energy level. So these white circles are acceptor atoms, that is aluminum atoms, and in the middle of EA and EV, that means acceptor energy level, and top of the valence band there is a energy level that is called Fermi energy level, which is denoted by EF, and the difference between the bottom of the conduction band EC and top of the valence band EV is known as forbidden energy band gap, which is denoted by EG. And these are aluminum atoms, okay, that are those are acceptor atoms which are present in the acceptor energy level, as we discussed earlier. Now when the temperature increases from 0 degree Kelvin, some of the valence electrons will go to the conduction band, leaving behind hole in the valence band. Okay, but there are very few electrons will go to the conduction band directly from valence band. Okay, so we are showing only 2 electrons will go to the conduction band. Okay, will leave behind 2 holes in the valence band. Okay, but most of the valence electrons, okay, from valence band will be accepted by acceptor atoms, that is aluminum present in the acceptor energy level. Suppose these 4 electrons will be accepted by, suppose these 4 electrons will be accepted by this aluminum acceptor atoms and will go to the acceptor energy level. So aluminum atoms will become aluminum ion. Will leave these 4 holes, okay, in the valence bands. So there are 2 types of holes in the valence band. One pair of holes is called intrinsic holes, and other ones are called holes left by the electron accepted by the aluminum. So these holes are formed when the electrons accepted by the acceptor atoms, that is aluminum atoms, and then aluminum atoms will become aluminum ions. And earlier the electrons, okay, the electrons have gone to the conduction band, will left holes in the valence band. On those those holes are called intrinsic holes. So valence band consists of 2 types of holes, intrinsic holes and holes left by the electrons accepted by the aluminum, whereas the conduction band only contains the electrons, those are known as intrinsic electrons. Okay, now we will see the quantity of electrons and holes. The quantity of holes, it means the number of holes present in the valence band here, is greater than the number of electrons present in the conduction band. It means that the majority charge carriers are holes in P type of semiconductors, and minority charge carriers are electrons. Hence, most of the current or conductivity is carried out by majority charge carriers, that are holes. And since holes are the positively charged, hence this type of semiconductor is known as P type of semiconductors. Okay, so whatever we have discussed in this energy level diagram, so this is the energy level diagram of P type semiconductors, and whatever we have discussed in the energy level diagram, I have quoted on the slide also. And I want to make one more point, that the difference between acceptor energy level and Fermi energy level, okay, is of 0.01 ev, electron volt. Okay, so this is the description of energy level diagram of P-type semiconductors. The energy level diagram of P-type semiconductors consists of one additional level, that is acceptor energy level, which is denoted by AEA, which is slightly above 0.01 ev from the top of the valence band. And when temperature is greater than 0, the sum of the electron jumps from valence band to conduction band, and the holes are produced in the valence band. These holes are known as intrinsic holes. But most of the electrons from valence band accepted by acceptor atoms, that is aluminum, and aluminum atoms become ions, and this process leaves behind holes, number of holes in the valence band. And the valence band consists of two types of holes, as we discussed earlier: holes left by the electron accepted by the aluminum, and intrinsic holes. So therefore the number of holes in the valence band are greater than the electrons present in the conduction band. So therefore holes are called majority charge carriers, since number of holes are greater than the electrons present in the conduction band. And there are few electrons present in the conduction band, hence electrons are minority charge carriers in P-type semiconductors. And as the current mainly carried out by majority charge carriers, that is holes, hence these semiconductors are called positive, that is P-type of semiconductors, since holes are carry positive charge. Okay, so this is the description of energy level diagram of P-type semiconductors. So today we have seen what are P-type of semiconductors, how they are formed, and the description about the energy level diagram of P-type of semiconductors. So thank you very much.